So this talk, my project, wouldn't be possible without open software. As a retiree, I don't have the budget for proprietary software. But it's a real mapping revolution. We're in a revolution now that we've been saying revolution for years, but it's still evolving. Is that better? Yeah. Okay, thanks. And also this open data paradigm that we live in is just fantastic. So I'm doing a hobby project. There's no money changing hands in this exercise that I'm going to outline. And you can see some of the contributors in terms of where I'm getting data from and so forth, and the sorts of data. My project is over in New Zealand, and in the Google Earth image you'll see the little yellow pin near the anti-meridian, but this is a town where I grew up called Gisborne, or alternatively Tairāwhiti. It's on a plate boundary. As you can imagine, plate boundaries have a challenge. And in the map on the right there is the area that I'm focusing on. But it's going to be a bit broader in time. Anyway, let's move on. So why am I doing this? What is the context? Well, being on a plate boundary where it's exposed to a whole range of natural hazards, earthquakes, the ground amplification effects, especially if you're on soft soils, active faults, landslides, tsunamis, mud volcanoes, and occasionally subtropical or ex-subtropical cyclones, and they have floods and landsliding, mass wasting, carnage. The area's really been hammered in the last few years, a whole succession of cyclonic activity. And of course that brings about economic impacts, political, cultural, etc. The geology is quite complicated, and the erosion in particular has really been accelerated since European settlement, and my forebears are a part of that settlement in terms of pastoral farming. So why do we need geological information or geoscience information to broaden it? It's important for land use decisions, building design, etc. And so my beef is to try to create data, assemble data in a way that hasn't been done before, so that geological interpretations and so forth are underpinned by a collation of data. So that's where the whole database comes into. And with modern data such as LiDAR, we're able to do things and all these technologies in a detail that we couldn't really do previously. So geological maps, the good, the bad and the ugly, as I say, just gives you an idea of some of the data that we're faced with. And there are all sorts of issues with traditional cartographic approaches to mapping, which I won't go into any detail, it'll become obvious. But things like the actual observations, where did people go, what did they see? Often that's not apparent in the map or in the associated report. Sometimes if you type in the grid references people put in, you find that they're wrong. So repeatable science is kind of my beef. And mixed concepts and mapping and so forth. So I'll just keep moving in the interest of time. So this is the scope. I mentioned that before. I seem to be going backwards. Anyway, keep on going. There we go. So we have a number of contemporary data sources that abound, but the top one, I'm the principal author of, was compiled at 1 to 250,000 scale using 50,000 field sheets. So it's quite broad. It's publishable. It's somewhat granular in that there are several layers there that one can interrogate and find out where data came from to a degree, but not very deep. And then I mentioned this LUC layer, which I don't have an image of, the land use capability, and it's just a single polygon file. with an explanatory text, but it's a recommendation what you can do on the land. But it's not granular. You can't break it down and interrogate all the components that were considered when it was made. And it didn't even consider, it preceded this map here. And so my geology map is a layer that wasn't used. So some major land use decisions are being made on data which is not really reproducible or testable. So this is one of my sort of beefs in terms of mapping, in that we should be breaking our data into layers such as bedrock geology, the superficial geology. So most geological maps are actually, the two are combined. So if you're interested in bedrock, but there's some quaternary on top of it, well, bad luck, because there will be a hole in terms of the understanding of what's underneath those shallow features. So my approach is to try to break things into as many layers as possible, weathering and duricrust being another layer, independent of those other features, artificial deposits and cuts, landslides. You'll find many geological survey type maps might have all of those compressed into one single layer. So it's one or the other. It's a real compromise. But if you do this, you can still make nice looking maps if a nice looking map is what you want, but you're not compromising the data underneath it. Okay, so in terms of compiling what I've been doing, a whole variety of maps going back to the 1920s, so over 100 years old, and various data sets such as the New Zealand Fossil Record File, petroleum reports, papers and so forth. I've been bringing them all together into a single digital medium. An example of an old petroleum report, this is what they look like. This is a 1940s example, there are earlier ones. And just trying to make sense of those, georeferencing them. When I combine a number of maps, I'm ending up starting to populate most of the streams where the geologist would have been, but one map on its own may not have, the geologist at the time may not have gone up every stream. So a combination of maps, bringing them together, means that we can provide a coverage over an area that is not apparent in any one map. The previous map was an example of an uncoloured earlier generation. This is a 1963 vintage map where it's been nicely coloured. This was done by BP, Shell and Todd, so they had some resources, nice maps. But what was really, probably better here to use that, is in the report is an inventory of observations. This is where they collected fossils, and not only did they collect fossils, they provided a description of what they actually saw in the field, such as the massive silty mudstone. So when you look at a geological map, often you get there might be a unit, it will have some broad statement about what it consists of, but there's also often a big variation. And so pulling this stuff out and adding that as point data means we can start to get a better idea of what's actually out there. And so once you do that, and there's a whole variety of other sources to start categorising them according to basic lithologies, you can start to see some patterns that may not have been obvious prior. And I mentioned the fossil record file. This is just downloading that file, and you see all those red points there. So there's a lot of data out there. Many of them have lithological information, some don't. I've had to clean some of them up. They're clearly in the wrong locations. But when you've got the original maps from, if there is an original map with a location on, then having that map georeferenced means I can fix many of them up. So I've been doing that, and that information will be going back to the custodians. Structural observations, another key data set in terms of the structure of the geology, the amount it's tipping, the direction it's tipping. so forth is key for understanding the distribution of rocks and how they made up. And in addition, the sort of geomorphic mapping that I'm doing, it's possible to get some of that structural information just by the form of the landscape. This is a dip slope where that red symbol is, and so you don't have to always be in the stream to find the outcrops. You can infer structure from images such as this, so having a recent LiDAR survey is just brilliant for picking this up. You can also see them on aerial photos, but the DEMs that you can produce from LiDAR is just fantastic. And then we have tools. These are QGIS plugins that can do all sorts of things, predicting where a contact might follow across the landscape, if you know where it is in one place, and then being able to test that. So where I might have inferred my boundary to have, in my earlier mapping, I can now test it with tools like this to say, well, actually, does it really go there if we assume a particular structural alignment, and so forth. Orthophotos. There's a whole catalogue of aerial photography in New Zealand, as there is in Australia and various states and so forth. We now have tools for creating orthophotos that are either by proprietary software or open source. I've been using this WebODM package with great success, and my workflow is in the PowerPoint there. So the orthophoto is a chance to go back into time. I've looked at thousands and thousands of air photo pairs in terms of photo interpretation, but to be able to stitch together hundreds of photos in a single process, might take an hour, is just fantastic. It wouldn't have been considered possible a few years ago. So I do the ortho rectification without ground control points. I just let the software just do its thing, and then I georeference it in QGIS, and it works. So here's an example where I've zoomed in. This is actually an ortho photo rather than a single unrectified photo, and you can see there are dunes and some flood deposits there. Exactly the same position, present day orthophoto or satellite image, whatever it is, been completely built over. So LiDAR is no use there because the landscape's been bulldozed and modified, we can go back, I can trace those beach ridges and so forth. Other data sources, just to mention, this is a really interesting one because those old photos that I just showed you were the basis of the mapping of the soils for this area. So I'm able to look at the same data that those Soil Bureau mappers were using and improve in terms of the spatial positioning of many of their boundaries, as in this example here where the Gisborne District Council have digitised those maps. Another data source is contributed by the New Zealand Geotechnical Society, and they call that the New Zealand Geotechnical Database. It's a web service, so there's collar files being served, and if you have permission, you can click on them and that will link you to PDFs. So I've been working through this Gisborne area where the flats, this particular scene is on some beach sands that are Holocene age, the last the oldest is 6,000 years old. And this graph on the right of the scene is a CPT, a cone penetrometer test log, which is basically a probe being pushed down into the ground, and it's a measurement of the resistance. So where you see the big kick in the signal there, that's the sand unit, this top level sand, and roughly about 5.5 metres down, it's gone through the base of that into estuarine muds, which are much softer. So there's quite a distinct boundary there. When you compile all of that, you can then start to interpolate, and I'll show you the results of that a little bit later. Other data sources, earthquakes in March 1966. I still remember watching the piano in our house going bang, bang, bang against the wall. So lots of earthquakes and reports based on that. Mapping and revision and so forth is what I've been doing. I'm sort of skipping quickly just to keep on time. And so in terms of sort of outputs and the units that I'm measuring, this gives you a bit of an overview of the floodplain area in Gisborne rather than the hill country, and some of the units that I'm using in terms of my classification. So using those all old orthophotos that I've created, using LiDAR, all these data sources helps me to improve the interpretation on what previous maps have done. So I'm able to get a reasonable accuracy that seems to work around about 1 to 2,000 scale in many places. It just to show you some of the wild geology in the hill country there. This is clearly a landslide. It almost passes as a glacial landform, but it's a mud flow. And what's actually special about this is it's come out of a mud volcano. So you can see, you should be able to hopefully see that there's a big flowing mass of porridge. So the mud volcanoes are not pervasive in the area, but this is an example. There's also lots of other mass wasting features of landslides and so forth that pastoral farming is occurring on. Much of this land has now been turned into forestry, and that is helping to some degree in reducing some of the erosion, but it also has triggering forestry practices are impacting when there's slash and logs and that left on the sides of riparian strips. The floods, rainstorms are washing that material downstream and knocking out bridges and so forth. It's a catastrophe. In terms of other scientific outcomes, the mapping of terraces along the river, that profile there where the blue line on the profile where we're linking terraces of a similar age based on tephrostratigraphy means that we can then derive down-cutting rates with time. Okay, so from memory I think there's something like a 3 millimetre per year down-cutting rate, so it's quite significant. So there's a lot of uplift, and with the climate drivers, these rivers are down-cutting fast. Thank you. I think I'm getting close. I talked about that geotechnical database. When you interpolate the base of those sands that I was discussing, then hopefully you can see those blue contour lines. So up in the top, the highest point there, the base of the sands are 10 metres above sea level, and when you get towards the bottom left, down to -10. So, and that's actually a measure of tectonic tilting. So that was once all sea level, and we're talking the last 6,000 years. So when sea level is roughly horizontal or stationary, we can get we can see a tectonic signal in there, and that's actually really just mapping that surface is really important, because from that you can make predictions on ground conditions where there isn't any drilling, and of course as more drilling is done, then the interpolation can be improved. And yeah, so my conclusion, as you can see up there, that we're just fantastic opportunities now with open source software and open data in the hands of people who understand what it all means. Practitioner expertise means that we can provide defendable, testable data sets, and if we use the right models, then it will allow for ongoing updates and improvements. And that's my talk, and I thought I'd throw in that thing, but from a 3D view of that mud volcano. So that's all. Thank you for your attention.
Okay, it's over to you guys. Has anybody got a question for Colin? Yes, thank you.
Thank you. Hi, my name's Mark. I'm from the University of Tasmania. I'm just interested in the geomorphological mapping. All those interpretations, are they done manually, or is there an automated or machine learning way of determining those different classifications?
Right, that's a good question. No, there's nothing automatic to it. It's all user experience interpretation. So I've been driving a mouse around the country. It's a great question, because there are a number of tools that are out there, raster processing tools. Geomorphons is one of them, and the rabbit holes, you never get what you want. They promise a lot, but I don't think the technology is quite there. But tell me if I'm wrong. It'd be nice to have some AI assistance, but no, that's all manually done.
Thank you. Any other questions? Well, then would you like to join me in thanking Colin for his presentation? Thank you.